So in this issue of the Developer Roundtable session, we have Daniel Ellison, also known as at Ziggurat, who was the, at least the implementer of the ENS's registry contract, which was written in LLL, Ethereum's low-level language. And as just earlier today, it was announced that that will be launching on May 4th, which is maybe a week away. I thought it was really timely and want to get more people aware and familiar with LLL right away. So we'll be publishing this as soon as I have the recording. Thanks, everyone, and I'll pass it over to you, Daniel.
Okay, thanks. This is my third week at Consensus, so I'm still new to all the procedures and things like that, but I'm getting used to it. And I'm really enjoying working with this bunch of people. It's been fantastic for me. This is sort of my dream job. I was doing this stuff outside of my work hours at my previous position, and now I get to do it all the time. So that's pretty fantastic for me. And I really appreciate Joe bringing me on board. Anyway, so I will get to it. I'm going to stop my video so you can't see me talking. And I'll share my screen. And go to the presentation. Can everyone see that?
Yep.
Okay, great.
Yes.
Okay, this will be a comparison between a contract implemented in LLL and the same contract implemented in Solidity. This is not a smackdown. Solidity is certainly more popular than LLL and will be for a long time, and it has a firm place in contract development. One would almost say a solid place. But I intend to show that LLL has a place in the Ethereum development world, and one that becomes increasingly important as the price of Ether rises. Please ask any questions you have whenever you want. I don't mind being interrupted. Okay. A couple of months ago, Tim Coulter tweeted, "What smart contract languages would you like to see supported by Truffle?" This was Joe's response tweet. LLL, of course, tightest compilation to bytecode, save big on gas. LLL, of course. Joe knows. Okay, let's get to the actual definition of LLL. It means low-level Lisp-like language. That may seem like 5 L's, but it's 3 because of the hyphens. And anyway, who really wants to say LLLL over and over again? Let's unroll that name a bit. This is just a quick overview. I'll get to details of each of these on the next couple of slides. So low level, hold on a sec. LLL has direct access to storage and memory. So you determine exactly where in memory or storage your data sits. You can arrange things to optimize storage use to decrease your gas costs. Speaking of optimization, you can arrange your code for the best use of resources. For example, say you have a data structure that you need to index into. If you move that data structure to the base of storage at 0, 0x00 if you like, the very first byte of storage, you avoid having to add the location of the data structure to the index, saving valuable processing instructions and bytes. Believe me, that really matters when you're trying to reduce gas costs to the absolute minimum. And that very thing was done when I was implementing the ENS registry contract. It saved a bunch of instructions. As I mentioned, LLL is one step above writing a contract in assembly. Oh, sorry, I'm on the wrong page. Yeah. Here we go. For example, say, okay, as I mentioned, LLL is one step above writing a contract in assembly. When you use an EVM opcode in LLL, it translates directly to the bytecode representation of that opcode. There's no boilerplate around it. There's no extra bytes or odd pushing and popping on the stack that automated generation sometimes does. All EVM opcodes are available to when you're writing a contract in LLL. Some examples are these: sload, store, where you're putting and retrieving data to storage; delegate call, which is how you would call another contract from yours in the context of your own contract. It's the way Solidity does libraries. And call data load is the way you retrieve parameters passed to your contract from elsewhere. And it does definitely produces smaller binaries than Solidity. As an example, I recently, as in a couple of days ago, re-implemented uport's registry contract in LLL. The Solidity implementation comes in at exactly 591 bytes, and that's compiled with the optimized flag. The LLL implementation compiles to 171 bytes. So in this case, the LLL version is about 70% smaller than the Solidity version. And that matters a lot when a contract can be accessed many times. And it also makes deployment less costly because the binary you're deploying is smaller and you're charged for the size of that binary. Okay, Lisp-like. So many parentheses. Here's a definition I made up just for you. Parenthephobia, which is an irrational fear of parentheses. Lisp and LLL do use lots of parentheses, and they can seem, fairly daunting. But they're mainly meant for the parser. It's one of the reasons Lisp-like languages are so easy to parse. But developers, either in Lisp or LLL, which is pretty well just me, generally use indentation to indicate code blocks, and they depend on their editors or IDEs to take care of the parentheses for them. Besides, you will get used to it. I mean, everyone has this, again, irrational fear of parentheses, but once you're actually doing some development in the language, they almost disappear over time. Let's see. Lisp and LLL use symbolic expressions and prefix notation. Symbolic expressions are a notation for nested list data. Here's a definition. This one's real this time, I didn't make it up. Symbolic expressions are a means of representing semi-structured data in human-readable text form, mostly composed of symbols and lists, and extensively used in the Lisp programming language, and of course, LLL. I'll be showing examples of this on the next slide. Prefix notation places operators to the left of their operands. So where you normally use 2 plus 3, which is called infix notation, most people don't realize that because it's the, quote, normal way of doing things, but it does have a name, infix. In LLL, you would use plus 2, 3. And it fits well with the use of symbolic expressions. And okay, anyway, I will go to an example of LLL code. This is a simple example of the equivalent of a Solidity modifier. There's no formal representation of modifiers in LLL, but as you'll see, we can very closely mimic a modifier's functionality. So first off, the easy stuff. Comments are delimited by semicolons. There's a bunch of rules in the Lisp world of how many you use in what context and how far indented things are. And you can look that up if you want to. And it's certainly not mandatory, especially considering this actually isn't Lisp, it's LLL. I do follow that to a certain extent, so you'll see it in my code. And there are the scary parentheses. As I said, you do get used to them, especially with a syntax highlighter that works properly. Okay. So def in LLL starts a macro definition. Macros can be used to clarify your code, and you'll see that when I do the code comparison. LLL macros aren't even close to the power of Lisp macros. They're more like C macros where they do a simple substitution. And in this case, we're defining a macro called only node owner. This will be used as a modifier to ensure that, perhaps obviously, only the node owner can execute a block of code. So when only node owner is used in the source, the macro will be looked up and its definition will be compiled into the bytecode. So this happens at compile time. There's no overhead on execution. So you have to keep that in mind though, because if you put in if you define a giant macro and use it a lot of times in your code, you're increasing your binary size by that much every time. So you just have to be aware of that. And macros can take parameters, multiple, but in this case, it's just the one, which is the node's ID that we're checking. And the rest of the code is what will be substituted when the macro is invoked. So when you use only node owner in your source, the part from when to panic is what will be inserted into your code, the bytecode version of it, of course. And you can also see the use of symbolic expressions and prefix notation. Everything is composed of lists defined within matching parentheses, and prefix notation can be seen with the use of the not equal operator. The operator comes first, and its operands follow. One of the operands, the first one is caller, which is the equivalent of Solidity's. I forget. But anyway, it's the personal contract. What's that?
Message.sender.
That's the one. Yes. And it just makes sure this is the equivalent, and after that is the is another macro I defined called getOwner. So you can see that it's easy to build up complex code, but keep it clear with the use of macros. Again, in this case, when the compiler sees getOwner, it'll substitute the source code of that macro at that point. So
what is node in this? Just wondering.
Well, this actually is taken from the ENS registry, and it's the ENS node that has been stored in the registry that is owned by a person who has registered a domain name.
It's a SHA-3 hash, right?
Yes.
So bytes 32.
Yeah, exactly.
Okay, cool.
Yep. Okay. So the body of this macro simply ensures that the entity calling the contract is the owner of the node that's being accessed. And the last thing there, panic, is the equivalent of Solidity's throw instruction. So it does exactly the same thing. And you can see the trailing parentheses, that just closes off the parentheses that preceded it. A lot of people like to put those on a separate line, but for me, it increases the code depth too much, sort of decreasing the readability. And again, I mean, the parentheses don't matter except that they balance. And they're used by the parser, not really relevant to a developer.
A quick question, Daniel. Did you implement panic as an invalid opcode?
It is a jump to an invalid location.
Okay. Yeah, so I think, that was the way that Solidity was doing it before.
Yep.
And then recently they did change it to an invalid opcode, I think. You know about that?
I'm not sure about that. I don't think I've heard about that, but this was added to the LLL compiler by Alex Bergzazi, and he actually added a new operator that defines a label that doesn't have a destination. So it does a jump to that label, therefore causing a panic. So I'll have to look into whether there's any new functionality that I should put into the LLL compiler. And as I mentioned, oh, sorry, go ahead.
Sorry, I just said thanks.
Oh, okay. As I mentioned, there is an actual LLL contract deployed on the mainnet, and that's Ethereum's registry, the ENS registry contract. It was written in LLL mainly because of the gas savings due to its size and the brevity of its code. That's it for the slides. I hope you have a better idea of what LLL is like now. Now I'm going to go through a contract written in both LLL and Solidity. But if there's any questions, you can ask them now. Okay, I will go to the source code. There it is. Okay, on the left, you see the Solidity version of the ENS registry. And on the right is the LLL equivalent. There's a lot of setup for the LLL version, which I normally keep in a separate macros.lll file. When you define macros, you're not adding anything to the size of your binary. It is entirely for the compiler when it's doing its thing. So you can have as many macros as you want and bring in as many files of macros as you want, and it will never increase the size of your binary until you invoke one of them. And at that point, it is just that one that gets compiled into the binary. As I mentioned, with LLL, you decide where things sit in memory and in storage. In this case, I'm using for the first two storage locations for storing parameters of the SHA-3 operator. And the call result is what you get back from calling another contract. So that's at position 40 in memory. Sorry, this is memory layout, not storage. And the equivalent of a struct is just defining offsets into whatever data structure that you want to use. So I just define them as 0, 20, and 40, so that when I use the offsets in code, I can use the word resolver instead of 0x00 or owner instead of 20. So it makes the code clearer. And that's, for me, the main advantage of using macros in the first place, is that you really clarify your code and shorten it, at least visually. So LLL and the EVM have no concept of functions. It is just a sequence of instructions that get executed. You have to, on the LLL side, have to handle that yourself. I've written a couple of macros to do that, so it becomes very easy. Oh, I forgot to mention that all contracts and any sequence of code that needs to be executed one after another has to be enclosed in a sequence operator. So you see the end of this is the end of the code. So the whole thing is enclosed in that sequence. So here's the precomputed function IDs. So with the ABI, you have to, the SHA-3, sorry?
Daniel,
Yep.
can I ask something here?
Yep.
So, yeah, I think, yeah, we know about these pre-computed function IDs. One thing I wanted to ask was the addresses that you're assigning to like in the struct and then in memory.
Yep.
It's like you've saved whatever 20, like the 20 hex difference between each one.
Yep.
Do you need to save that much, or
With
yeah? What I'm wondering what the reason is. If you use 10 instead or 30 instead, what the difference would be?
I guess 20 is the size of an address. 20
Yeah.
bytes.
Yeah.
But I didn't get the memory layout.
Also an address, yeah.
But yeah.
Yep. It's
Okay, how about in the memory layout? Is it the same thing?
Yeah, that's
Why is it
the one I didn't get also.
Yeah. Again, actually, I think this is a typo that has been fixed in the real thing. It should be 0, 1, and 2 because storage is in chunks of 32 bytes, whereas memory is in single bytes. So this should actually be 0.
Okay, so that's good to know there.
Yeah.
And I missed what was said about memory. It
And
was
memory
a gap of 20.
Yeah, because memory is referenced by byte. So if you put something at 0, like a 32-byte address at 0, it takes up 0 to 1F, or 0 to 31. And the next thing would be, in this case, label bytes at 20. So you have to set aside enough room in bytes for what you want to store in memory. As I said, storage works differently. It is accessed by 32 bytes.
Yeah, by 32.
Yeah.
By chunks.
So you
can. So sorry, in memory.
Yep.
So in memory, they're like addresses. Is that why there's a 20 difference between each one?
Yeah, there's 20 bytes different between each because you reference memory by bytes. So you can, when you say you want to reference 0, 1 in memory, it's only 1 byte away from 0, whereas with storage, if you wanted to access 0, 1, it's 32 bytes away. So that's the difference. That's why you have to.
Okay, so a label bytes is kind of like a label address. Is that right? And node bytes are kind of storing address.
Well, they have nothing to do with the layout of the memory. They're parameters to the SHA-3 operator, which takes 2, or can take as many as you want. But in this case, I'm using 2 32-byte parameters to do the SHA-3. And they have to be in memory for SHA-3 to access them. So you can't just, you can't do a SHA-3 of anything in storage. It has to be put in memory and then executed. So that's why those are there.
Okay, got it. So that's clear now that's for the SHA-3.
Yep.
Yeah, that macros to help the SHA-3 call. Okay.
Yeah.
Maybe yeah, I guess that would be clear if someone read the code, but I guess if they haven't read all the code at the bottom,
yeah,
maybe it might be clear to mention the use of those.
Okay. And here's the definition or the place where I used those 2 locations. So Mstore puts data in memory, and plain Mstore actually puts 32 bytes. There's Mstore 8, which puts 1 byte. So by doing Mstore node bytes, it's putting the value of node into node bytes, 32 bytes worth. Same with label bytes. So you can see that this calculates the record location for the node and label passed in. So node is the parent node and label is the hash of the subnode label. This requires understanding how the registry works, but I'm going to kind of keep it more high level than that so that you can get a feel for how things are implemented in LLL as opposed to Solidity, not so much the mechanics of the registry itself. I mean, I can do another presentation on any of this if there's interest. Okay. Joseph, you said that you guys already know about precomputed function IDs?
Yeah, I think yeah, most probably have seen the ABI.
Okay.
So you're just making these hard-coded. It was
Yeah.
touched a little bit on last week's with Alex as well.
Okay, yeah, that's right, actually. So
I was finding it useful, but I'll shut up and let you devs keep going.
okay, I'll do it quickly then. The ABI specifies that you have to encode the function signature that you want to invoke or call as a SHA-3 hash, and you only use the first 4 bytes of that as the identifier for the function that you want to invoke in the contract that you're calling. So in this case, in the very first line, you can see that the Solidity version of the contract function call would be the owners, and the parameter would be the bytes 32. So you take all the spaces out of that, which in this case there's none, but if you look down, there's a couple that have multiple parameters. You take that string that you've created and do a SHA-3 hash of it. You get a really long hex number out of that, and you only take the leftmost 4 bytes of that, and that becomes the function ID that you provide to the when you make the call. So it's a way to identify the function in a consistent manner. And these are per contract, so there's very little chance of hash collision.
To parallelize that with Solidity, that would be the equivalent of just setting a storage var public, right? The getters and setters that get set up automatically.
I don't think it's related to that. It is more about the mechanism of calling a function on a contract. This is what the ABI specifies. So I've had to...
Sorry, didn't see the comments on the right. Yeah, those are the actual functions that you're writing below.
Yeah. Yep.
So, yeah, cool.
Yeah, so 1, 2, 3, 4, 5, 6, 7. There are 7 functions in the registry contract, and you can see there's the owner function right there. And you see it just returns the owner of the node that's been passed in. So it returns the, yeah. And I'll be showing, what's that? Okay, I'll be showing the...
I had a question, but continue.
Anyway, I'll be showing the LLL implementation of that owner function in a couple of minutes. Did somebody have a question?
Yes. So you adjusted the struct record, Daniel. So I wanted to check with you because I checked the master branch of ENS right now.
Okay.
And it does not have the fix that you just made here in our presentation.
Yeah. There's no problem with that. For one thing, storage is sparse. So it...
Yep. Okay, got it. Yes.
It only uses... Yeah. And that's the other thing I should mention about memory. If you store something at 0, like in node bytes here, and then you define something at FFFF, you are paying for every byte between 0 and FFFF. Whereas with storage, you are only paying for the storage locations that you set. You don't have to, like, you can actually,
And I've also read that you pay quadratically for each word that you increment, right?
yeah. So it's okay that those definitions are like 0, 20, and 40 because it really doesn't matter. It's really semantics. I will fix it.
Agree. Thanks.
Yep. So these are the 7 functions that are implemented in this contract. And this is a utility function that I put together that, as it says, shifts the leftmost 4 bytes of a 32-byte number right by 28 bytes. So you get a 32-byte number that might be, let's see, shift right. Where the first 4 bytes you want are the function signature, the function ID that I was describing previously. These things here. So you get this passed in, plus the rest of the 32 bytes has data in it as well. So you've got a 32-byte number, whereas in which the first 4 bytes are the function ID that you want to extract. So this helps with that by taking that and shifting those leftmost 4 bytes all the way to the right, and it's 0 fills on the left. So you end up with the function ID isolated. And you can see here that it takes input, which is very descriptive, and does a shift by dividing the 32-byte number by 2 to the 224th. So that is the equivalent of shifting right by 28 bytes. It is a bit expensive, but it is, I mean, in this case, it's done just once per function invocation. The next one is the convenience macro that I put together to make it a lot easier for people to understand LLL code. You can see that I've defined function, and it takes two parameters, function hash and code body. So it determines whether the supplied function ID, the function hash, matches a known function hash, which is what we defined above, and executes the code body if it does match. So you can see that it does a test for when the function hash that has been passed in matches the shift right, which is that macro I just showed you above. Call data load retrieves the data that was passed in from the function call. So call data load 0 gets the first 32 bytes of the data that was passed into the contract. So, and then we take that and shift it right, and we isolate the function ID that was passed in. Function hash is passed by when you invoke the function, when you invoke this macro, which I'll demonstrate right now. So you can see function get node TTL. If you see that, then get node TTL is just a macro which substitutes that ID. So when you call it, in this case get node resolver, it's passed to this macro as function hash. And so in the end, what this does is it gets the function hash that it needs to compare to. It accesses the data that was passed into the contract call or the function call and compares the two with equals. And if it is equal, if the function ID that was passed to the contract matches the function hash of the function we want to execute, it does execute the code body. If it doesn't, it just falls through to the next piece of code in the source. Anybody have questions about that? I know it's quite unfamiliar to everyone, this format, but I think when you really pull it apart, it becomes a little more clear. Okay, so I'll go over this macro, then I'll skip a bunch of the macros because they're fairly similar, and I'll get to the actual function definitions. Okay, this macro calculates the record location for the node and label passed in. So the way the registry works is you hash together two pieces to find out where the actual record is stored in the registry. So here we use GetRecord. It takes two parameters, the node and the label, and see it's enclosed in a sequence because there are multiple lines to execute. So you can see that that's enclosed like that, and this one is that. So Mstore stores in memory by default 32 bytes. In this case, the first case, it stores it in node bytes, which I've defined as 0, and it stores the 32-byte node ID. And the second one puts the label hash, or the label into the label bytes memory location, 32 bytes. And then SHA-3 requires a memory location to do its hashing. So I point to node bytes and tell it how many bytes to hash, and it does that. So it will return the single hash of those two things. Okay, so just a note that sload and sstore do the same thing for storage. And again, 32 bytes. But as I mentioned, there's an 8-bit version of this that you can use. And I've only used it when doing end-to-end tests for the LLL compiler. I used it as an example, as a test parameter. So it's not used often, but it's certainly available.
And it costs more gas, right?
Yes. Oops.
So, sorry, what was that comment about Gonzalo made? Gas?
Well, the Mstore costs more gas than Mstore 8 because you're only defining one byte with Mstore 8. So if you plan it correctly, you can compress your own data into a smaller, like into a 32-byte thing. You can have several definitions in there, and you can pull them apart or access them. What's that?
Yeah. Yes. Yes. You can. Yeah. You're right. You can access just by byte memory.
Okay. Okay. I'll get to the actual init section, which is the equivalent of Solidity's constructor section, or constructor, period. And in this case, all I'm doing is using one of the macros I defined to set the owner of the root node, which is the base of everything in ENS, to the entity that deployed this contract. So this happens at deploy time, and anything you do in storage when it's being deployed persists when you execute the contract itself. So this happens at deploy time, but it does set a storage location to the caller of the contract, which effectively sets the owner of the root node. And now we're at the code section. LLL has a couple of convenience macros that have been predefined in the compiler itself. One of them is return LLL. It's a bit hard to describe right now, but it just simplifies the invocation of the contract itself. So up here you can see that the constructor does that, and then it falls through and does return LLL. So what that does is return everything between these parentheses as bytecode to whatever is doing the deployment. So it'll come through, it'll do set owner, caller, and then it'll compile everything between these parentheses and return it to whatever called this so that it can be deployed on the blockchain. So the only thing that gets deployed is the stuff between there, not anything that happens in the constructor, which is the equivalent of Solidity. The constructor is executed once and can never be executed again, and this is why. It is just not there after the contract has been deployed. Okay, so, and again, it's all in a sequence because it needs to be according to how this works, or how it works. The first function is called getNodeResolver. So it returns the address of the resolver for the specified node. And that will resolve the contract name or the ENS name to the contract address or whatever it's pointing to. But for the most part, is to resolve, to do what DNS does, take a human readable name and convert it to another form. DNS is IPs, and here we're using contract addresses. So let's see. So the signature here is resolver bytes 32, like you saw it previously. And it takes a node as the input parameter and returns the resolver that is responsible for this node. So it can do that translation between name and contract ID or contract address. Okay, so the function macro is invoked here, and it takes getNodeResolver, which is another macro that just defines the ID of this function. And that will, this macro function will execute this code if the node address passed in matches getNodeResolver. So call data, I've just defined this convenience macro here so that it's easier to read the code below it. Otherwise, you'd be seeing call data load 0x04 instead of the word node, which is down here. So I use it over here. Oops. Okay, so it's in a sequence, just like everything else. You get the node's resolver and save it. So I'm using the getResolver macro, which indexes into the storage structure and retrieves the resolver address for that node. And I'm doing an Mstore into call result of the result of this macro call. So it executes getResolver node, that returns the node address, the resolver address for that node, and that is stored 32 bytes into call result, which is at OX40 in memory. And that's because the return call requires a memory address and a length for how long, for where and how long the return data is. So that's what this does. It returns 32 bytes at 0, or at 40 in this case, which is call result. Any questions about that?
So it returns 32 bytes and then goes to position 40? Is that?
Yeah, it returns
It returns the 32 bytes from position 40.
Yes, it returns the data at call result, which is 40. It goes there and accesses it and returns 32 bytes there. So
okay, so the opposite of what I said. It goes to position 40 and gets 32 bytes. And returns.
Yep. So that will be the the resolver address for the node that, the ID of the node that was passed in. So that's the way when you're doing an ENS lookup, the first thing you do is, given the node, you go and find the resolver for that node, and then you get that result back and you call the resolver to get the mapping from the ENS name to its contract ID. So it's a two-step process, but this is the first step where it just returns the resolver for that node.
So I was wondering, yeah, about this two-step process, because the GetResolver node already gives you the value, right? And then it seems like, yeah, you've got to put it in memory first before then you can return it. Is there a way that we could have just done it in one step or something?
No, because the return requires that it be in memory. So if this returns an ID to when it's called, so GetResolver returns an ID, but it's not in memory. It's a return. It's a value that is just defined. It needs to be stored somewhere. So I could store it either in storage or memory, but in this case, it has to be memory because that's how return works. It takes the value.
Yeah, it seems like that there's some kind of like temporary memory, which is what GetResolver node, that's where that value is put. But we don't, but we got to store it in actual memory before we can return it. I see that.
Yeah. Okay. Okay, so get node owner. Let's see. I just want to check something. Yes. Okay, the next function that can be called on the ENS registry is called getNodeOwner. I think I was going to show the equivalent. So, So I've called it getNodeOwner to be clearer, but the Solidity version is just called owner. And you can see that up here, I've got the signature, which is the same as the actual signature of the Solidity function. Okay, so again, I define a macro for node that simply equates to call data load 4. The first 4 bytes, of course, are the function ID, so the next piece of data that's passed in is at 4 in the call data. So by doing call data load 4, I get 32 bytes from position 4 in the data that's been passed in. And that is defined as node, so I don't have to do the call data load every time. And it helps further on in more complex contracts to have these as macros that are invoked. Instead of having call data load 04, it's a lot easier to read. And in more complex functions, it makes even more difference, makes it more clear. So it does the same thing pretty well as the previous function, but in this case, it returns the owner of the node. So as opposed to getResolver, we're just getting the owner. So it does exactly the same thing. It stores it in call result and returns it. So it's pretty simple. It's as simple, really, as this when you think about it. Returns records node owner, and that's all that this does. It returns the owner of the node. You can see why this was a good candidate for being done in LLL, because everything is quite small. So it compiles down to a much smaller size than the Solidity version, because Solidity has a lot of overhead. Again, because it's being generated and it's a more complex language with typing and everything, there's a lot more around the code that you actually want to execute. Whereas with LLL, it's a lot closer to the equivalent in bytecode. And in fact, as I mentioned, every EVM opcode is available in LLL. And an example of that is actually return. Return is, this translates exactly to a return that you would do in the EVM. It's just done the other way. So in the EVM, you would see 32, and then you would see 40, and then you would see whatever the opcode ID of the return character is. So that this line compiles down to 3 opcodes, or 3 things in the binary. So it compiles down quite small, and there's other examples of that type of thing.
I've been looking at, I guess maybe I'm challenging you a bit, but
Yep.
or just maybe throwing an extra fact, bit of info, but I ran the ENS test suite yesterday, and there's a gas report generated for each contract. And so ENS.LLL's, the full test suite costs 79,022 gas.
Yep.
And ENS.Sol costs 80,034. So it's like a difference of 112, and like quite negligible.
Yeah, I'm not sure.
I think it's been, as I understand it, the Solidity version has been significantly optimized since the original LLL implementation.
That is odd, because I know for a fact that the LLL binary is about 30 to 40% smaller than the Solidity, the equivalent Solidity binary. So that alone, I mean, you would save gas on deployment, but I'm not sure why the test suite has such a high gas usage. I don't know if it's what has been done in the test suite or how many times it's looped or whatever, but I'll ask Nick about that. But I know that the binary is much smaller. There's less opcodes, so it has to be cheaper, and I'll bet it's actually a lot cheaper than you're getting in those tests. But I'll confirm that, and I'll put it in the developer roundtable Slack.
Yeah, take a look. I'd love to hear from you on that. And then I guess, yeah, at the hour, of course, I'm not going to stop the meeting if there's like more good discussion happening, because we put so much time into getting to this point for good discussion. I'll probably stop the recording on the hour.
Okay.
The other thing I was going to say is, yeah, I was talking to Nick about basically like saying, you know, I'm worried about launching, or like that this is written in LLL, which has a very small community and small number of reviewers. But in his defense, which was fairly well reasoned, is he said that most of the review, it seems, has been done on the assembly code, and so he, Martin, and yourself have reviewed that assembly code.
Yes, exactly. And what I'll say about that is, yeah, there is a slight security risk because there are no automated tools to do it, and you can't do it in the block explorers, and there's only like one person or two people who really know LLL to any extent. But that's actually one of the things I'm trying to mitigate with this presentation, to get more people on board. And I'm pretty sure most Ethereum developers don't even know that there are alternative contract development languages aside from Solidity. So that's another thing I'm trying to get out there, that there are actually other choices. Also, LLL contracts have so far been pretty compact. In the case of the ENS registry, it is very small, and as you said, people have verified the bytecode, and I've also looked at the assembly output of the LLL registry compilation and verified it there as well. So you can do it at the bytecode level, and you can do it at the assembly level. And hopefully there'll be more people coming to this who can eventually do a visual verification as well. I'm actually doing a lot of work defining end-to-end tests for the LLL compiler to ensure that things are functioning properly and that nothing breaks when there have been changes to other parts of the Solidity repo. That actually did happen once already before the tests were in place, where, as I mentioned, Alex Bergzazi added the panic keyword into the LLL compiler, and a change that someone else made to the assembler broke the panic keyword. So needless to say, there's a test in there now, and I've written about 14 or 15 other ones, and I plan to write like dozens more. So that's another way we'll know that, or it's another thing to keep in mind, knowing that the compilation went properly. I'm also going to start looking at adding formal verification to the language using Y3, which is a system that converts your source code to another representation that is more easy to verify. There's already an effort to verify Solidity contracts with Y3 by Pira or Yoichi, but so far only a small subset of Solidity is supported. It's not going to be easy to do the same with LLL because it's so hard to do with Solidity already. It's sort of not the holy grail, but it's what everyone wants to happen. It's just really hard. So it's not easy to do that the same with LLL, and I'll definitely need lots of help, either within consensus or talking to Yuichi or any volunteers that would like to help. So I don't think there's anything different in the rest of the code. It was pretty straightforward. The only thing I'll say is that to emit an event, you use the log command. There's log 0 to 4, depending on how many parameters you provide to it. So you use log 2 to provide the signature or the hash of the event's signature and the node and the node that was affected. So in this case, a transfer of ownership was executed, and the new owner is in call result. So that is given at the beginning of the log, and then the SHA-3 of the signature, and then the old node right there. So, and stop just stops execution. And let me see. Yeah, it's all pretty well the same. So hopefully you have a better idea of what it's like to develop contracts in LLL. I'll definitely do more of these. What's that?
You definitely should do more.
Okay, yep, no problem. I hope it was effective anyway, or gave you a... Pardon? Oh, okay, I think
Quick question about the log 2 of code there. So it takes like data and then the size of the data and then the same thing, is that right? Yep. That's why it has 4 arguments?
Yes. So log 2, the 2 just means 2 indexed entries. If you know about Solidity events, you don't have to specify the event signature. It's done for you, but you do give indexed and non-indexed parameters. So the non-indexed, as you can see here, non-indexed is UN64 TTL. So it's the time to live for this particular node. But that's beside the point. You store it in memory and then do the same thing with the return as the return did, where you provide the memory address and how many bytes. And the next parameter is it's kind of, I won't go through how this is defined, but provides the SHA-3 of the event signature, which is necessary for when you're looking up events or when you're waiting on events. The SHA-3 of the signature is what you do identify it by. So, and the last note I'll make, because there are no functions, what you just saw is a complete sequence of events or sequence of instructions that get executed. And it'll stop up there, or it'll stop here, or it'll fall through. And this is the equivalent of Solidity's fallback function. You can do whatever you want here, but in this case, it just throws a panic because nothing matched. So you called a function that didn't exist or the contract didn't know of. And that's it. I'll stop sharing.
Okay, one last question about the log2 opcode there.
Yep.
So how would it look if it wasn't indexed?
Well, you always provide.
The node was not indexed. How would it have looked?
It would be like this. You would do that, and then all you would do is take this off. Oops. So you would have the non-index parameter, and then you have to provide the SHA-3 of the event.
Oh, okay.
And that's it.
Yeah, wait, no, I meant, but Daniel, instead of, so right now we still want the node to be logged, but instead of it being indexed, we just want it logged.
Oops. Only one thing can be indexed, can be non-indexed.
Only one thing can be non-indexed.
Just the very first parameter. And the rest is the equivalent of the indexed specification in Solidity. And same with Solidity, you can only have one be non-indexed there too. In this case, it's a TTL. But you can have up to 4 index parameters, in which case you would just use log4 and provide all the rest.
Wait, so the node there, you can have an event, and some people make this mistake where nothing is indexed. So bytes 32 node would not be indexed. How would that? Is there a way to do that? Yeah, some people don't have that indexed keyword in there.
I would think it would throw an error on compilation, would it not? I haven't done it myself. So
you're saying that EVM always requires at least one parameter to be indexed, is that right?
No, actually, it requires that only one be non-indexed. Anything else you want to provide to the event has to be indexed. So, and you can have up to 4 of those.
Okay.
In this case, it's 2. It's the SHA-3 of the event signature, and there's the node address. And you always have to provide that. So in Solidity, you can only provide 3 because there's always one represented by that in the event when you look at it in the transaction receipt.
Is Solidity automatically doing the indexing then if you don't add the keyword?
I was wondering that too. Could be.
I don't think so. I think if I were writing the Solidity compiler, I would insist that there's at least one non-indexed, and if there are more than one, throw an error. But there can be 0 indexed. Doesn't matter. You can just have this be the result. And in our case here, we have to provide that. But I would have to think that Solidity, on seeing 2 parameters that are not indexed, would throw an error or a warning or something, because there's no way it can provide more than one non-indexed parameter to the log call, because event eventually calls this in the EVM, because log 0 to 4 are direct analogs to EVM opcodes, and they take exactly these parameters.
Yeah, I definitely know that I've written a lot of like events, log love events without using the index keyword. So
Okay. Okay, that's odd because, and so I guess that means well, I guess it would have to arbitrarily choose the first parameter to be non-indexed and then make the rest indexed. To me, it should have, thrown an error.
Yeah, so that's an interesting thing about Solidity. Then we can ask them for clarity or something, what they do. Thanks.
Yeah.
Yeah, that's a good example of the value of looking at different languages, I think, because it exposes these different layers of abstraction.
And if nothing else, it explains what's going on behind the scenes with Solidity itself. Like
Yeah.
you know now that it's actually calling the EVM opcode log 0 to 4. And it's doing the SHA-3 of the event signature for you. But now you know that happens.
Cool. All right, awesome. Now I'm stopping the recording.